Hello everyone. So today in this lecture we'll be discussing about a problem from nbpho again, and this question is from the topic of thermodynamics. The question says liquid helium. Liquid helium is cooled under low pressure by vaporizing it and pumping the gas away. The heat of vaporization of helium is lambda is equal to 22 kilojoule per kg, which you can take it to be constant. The specific heat capacity of the liquid C as a function of time is shown in a larger graph, and we will be using this graph only for analysis. What fraction of liquid helium has to vaporize to cool the remaining liquid from T0 is equals to 4.1 Kelvin to T1 is equals to 2.3 Kelvin. Now first we have to analyze the situation. If you read the first line, it says that the liquid helium is cooled under low pressure and vaporizing it and pumping the gas away. And this small line indicates that the process is carried out quasi-statically, or the at each step of the process the gas is at thermal equilibrium. Means that suppose my liquid helium is at some temperature T and some dm mass converts into gas. Okay, the gas is immediately pumped out, and the remaining liquid helium, the temperature decreases to some temperature T minus dT. Thus, we have to assume that the process is quasi-statically, as nothing is mentioned about the process doing it suddenly, and it's also said that the pumping the gas away as soon as some amount vaporizes. Suppose at some temperature T, the mass of liquid helium available is m. So I can write minus dm into lambda. That is the heat of vaporization which is absorbed in form of heat from the liquid is equals to m into c into minus dt. Cancelling minus both sides, we'll get dm by m into lambda from initial mass to final mass is equals to c dt integral from initial temperature to final temperature. You can also write it as lambda times integral final mass from final mass to initial mass dm by m is equals to integral from time final temperature to initial temperature c dt. Final temperature as mentioned in the question is 4.1 Kelvin, is 2.3 Kelvin, and initial temperature is 4.1 Kelvin. So basically integral c dt refers to this area. Where is 2.3? 2.3 I guess is somewhere here, and 4.1 I guess it's somewhere here. How to find this shaded area? Do this will be using some approximation and a little bit of tricks. So we'll be considering this trapezium at first. This is trapezium 1, and this has area suppose delta 1, and suppose this is second one, this has delta 2. So we can approximately assume that this area which is extra counted can be almost compensated by this area which we are removing. And what is delta 1? Delta 1 is equals to it's about 4.1 minus 2.6 half into what is which number does this corresponds, it's nearly 4.5 into 4.5 minus 2, and if you evaluate it, it will come out to be 1.5 into 2.5 by 2, which is 1.875. First equation. And what about delta 2? Well, there's some problem. Yeah, here it will be 4.5 plus 2 whole divided by 2. So it will be 1.5 into 6.5 divided by 2, and which will result you about 4.875. Similarly, delta 2 is simple to calculate. It's just 2 into 2.6 minus 2.3. That is 2 into 2.6 minus 2.3, and it's about 0.6. So integral CDT is nearly 5.5. First equation. Here's now we'll put this in this equation that will come ln mi by mf into 22 is equals to 5.5. 11 5s are 55 and 11 20 it will come out 4. So mi upon mf is equals to e to the power 1 by 4. Just putting it into the calculator, we get e to the power 0.25 as nearly 1.25. So vaporized mass will be mi minus mf, and total mass will be mi. Answer will come 1 minus mf by mi, which will be 1 minus 5 by, 1 minus 1 by 1.25, nearly 0.2. So 1/5 of the helium liquid vaporizes to bring temperature from nearly 4.1 to 2.3 kelvins. So exact answer as per nbpho answer key is nearly 2.1, 0.21. So it's close to the answer we got. Hope you enjoyed it. Thank you. Have a nice day.